Hello everybody, in this video we're going to continue our story of understanding how the planets move in our solar system and how things orbit in general. What makes things in the universe move and how is their movement controlled? What force is really behind the movement of objects? So we have left off by going through Kepler's 3 laws of planetary motion, which are just absolutely fantastic for things that are in orbit around our sun. However, they break down and they can't be used for how things orbit in general. They don't give us the how of how things orbit, how things move. They just give us a prescription, a set of laws that we can use, mathematical relationships that work for things in orbit around the sun. We want to understand orbits in general. And for this, we're going to have to move into the era of modern experimental science. We also still have a few vestiges of geocentrism. Yes, the geocentrists at this point in history are still hanging on, even after Kepler comes out with his Keplerian view of the solar system. So we got to finally put that one to bed, and we can do both the birth of experimental science and finally put the last nail in the coffin of geocentrism by looking at Galileo. So Galileo Galilei, I have the dates there. We're at 1564 to 1642. You never have to memorize dates for this class. I really do enjoy the history of things, and I think it's a wonderful thing to know and know exactly how things were or when things were being figured out and actually see the pacing of scientific discovery. Adds a lot of context to what's going on. However, you do not need to memorize dates at all for this class. I want to talk to you about Galileo Galilei because in our story of understanding the universe that we live in and actually accepting a Copernican view, a heliocentric view of the solar system, a sun-centered view of the solar system, and just starting to understand how nature is going to work, we have to go to Galileo. Galileo is often called the father of modern science because he was not the only person doing it at the time, but definitely the most prolific and the strongest advocate for actually observing nature to come up with hypotheses about how nature might operate and then doing an experiment to test this hypothesis. Sort of the foundation, the first person to really apply the scientific method to observe nature, to understand nature. But not only that, he was also famous for being the first person to take a telescope, not invented by Galileo, a common misconception. Lippershey invented the telescope, but Galileo, soon after the telescope was invented, realized he could take this wonderful invention and turn it towards the heavens to do observations of celestial objects and understand the nature of the heavens by observing the heavens. And it's with his telescopic observations that the heliocentric model is going to just clearly win over the geocentric model. It's going to be really, really hard to keep hanging on to an Earth-centered model, even though Galileo did get into a lot of trouble with the Catholic Church over being a heliocentric proponent and publishing things that promoted a heliocentric model. Okay, so let's dive into what Galileo Galilei did. And I want to start with his telescopic observations. And the first ones we're going to look at really just go towards, they fight off geocentrism or they counter geocentrism by really countering Aristotelian idealism that everything in the heavens must be perfect. So one of the first things he does is he has his telescope, he points it, he looks up at the moon, which I encourage everybody to go out and observe the moon. If you have binoculars or a small telescope, definitely take a look at the moon. It's absolutely stunning, even with a small telescope. So Galileo, with a small telescope, looks at the moon, and he notices that the moon has mountains and craters all over it. Here we can see some drawings of his. This is in Sidereus Nuncius, the Starry Messenger, published in 1610, probably one of the most famous books in all of science. And here are his sketches that he made of the moon. And you can see that he observed lots of craters, mountains, things like that. He very quickly realized that the moon is not this perfect sphere. And remember that Aristotelian idealism, everything in the celestial realm outside the earthly realm must be perfect, no blemishes allowed. And here we have a blemished moon. And you know what? You're probably thinking, I go outside and I look at the moon, which I'm sure you all do all the time, and I can see there are bright spots and dark spots, the so-called man on the moon. What is absolutely astounding, and it just shows how deeply ingrained Aristotelian thought was and dogma was for the people think about this at the age is they believe that those differences, what you actually are physically seeing with your eye when you look at the moon, that you see these dark spots and light spots, they thought that must be an optical illusion. It must be some imperfection related to the human realm, while the moon itself is perfect. They weren't even believing their own eyes. Hard to argue with a telescope, though, where you can actually see craters. Like, yep, that's a blemish. Nothing you can really do about that one. So he notices that the moon has craters and mountains. The moon is not a perfect orb. He turns his telescope and looks at the sun. And you might think, that's a terrible idea. You shouldn't stare at the sun, especially with a telescope. You'll go blind. So Galileo was no dummy. He would wait until sunset on cloudy days and observe the sun through clouds near sunset when it's dimmer. But that was still too much, so he actually invented a projection system where he could have the light pass through his telescope and then project it onto a sheet and project an image of the sun. And using that, he did sketches of the sun. And one of the first things he noticed is that the sun has blemishes. It has these dark spots, what we now call sunspots, related to the magnetic field and the magnetic activity of the sun. But he notices there are sunspots on the sun. The sun's not a perfect orb either. The sun is blemished. And more than that, so these are drawings from 1612, June of 1612, and here's the date. So you can see day after day, he notices that this pattern of blemishes remains the same, but it moves, it rotates. The sun is rotating. So now, this object, the primary object of the heavens, the sun, is not even perfect. It has blemishes, and we can tell that it rotates. It's spinning around and around and around and around. Things that weren't part of the geocentric model. So absolutely foundational, amazing observations, a lot learned from these, but maybe not the ones that really, really give it to geocentrism. So let's get into one of those. Using his telescope, Galileo looks at Venus. And he looks at Venus over a long period of time. And what he's going to do is he's going to document the phases of Venus. He's going to see what phase of Venus can be seen from Earth. And he, over time, documents, he sees Venus going from the new phase through a full cycle of phases back to new. So from new, waxing to full, and then waning back to new. What is incredible about observing a full set of phases for Venus is this is impossible with a Ptolemaic geocentric model, any geocentric model. Yet it is a simple prediction of a heliocentric, a Copernican model. Let's have a quick look. So in the Ptolemaic system, here the sun would be the center of everything. And if you're looking out, you would you end up with sort of this geometry as you look out at the deferents. So you'd have the sun's deferent, and here you would have Venus. But you would only could observe crescent phases. You can draw this all out, but the Ptolemaic model does not predict a full set of phases. It pretty much just predicts crescent phases. Galileo actually takes a look. Does that hypothesis hold water? Or does a hypothesis of a Copernican model, where you can see a full set of phases, where now the sun, Venus is orbiting the sun, and Earth is farther away from the sun. So as Venus orbits around, you will actually see a full set of phases. Here you'd see a new Venus, over here you'd see a full Venus. So a heliocentric model predicts a full set of phases, which is what Galileo observes. Geocentric model predicts something else. Heliocentric model predicts a full set of phases. Which one are you going to go with? The one that works or the one that clearly doesn't? This is a huge blow to geocentrism, because now we have observations that contradict predictions of the geocentric model. And conversely, we have observations that confirm predictions of a heliocentric model. Okay, that's a pretty big blow. We're not done yet. A fourth observation that he does is he turns his telescope towards the planet Jupiter. And he starts looking at Jupiter, and he notices that he can see Jupiter, and then he sees these little tiny bright stars next to it. He actually thought they were stars, but we haven't really differentiated planets from stars really that much yet. Then he sees these little bright points next to it, and he starts to document them. And here's from Sidereus Nuncius again, the Starry Messenger, where he is putting where he sees the dots, and he notices that they are changing their orientation night after night. Being as clever as he was, Galileo is like, holy crap. Here's our planet Jupiter, and it has 4 moons. It has 4 objects that are orbiting around it. Now realize the geocentric model has something absolutely foundational to it. The Earth is at the center of everything. Galileo here observes that Earth is not the center of everything. Here's Jupiter, that's its own center of its own little system of moons, the planet and moons. Another huge blow to geocentrism. Perfectly fine. In a heliocentric model, the Earth has its moon that goes around it, so why can't another planet have moons? And then he did make a 5th observation. This one doesn't really go with the geocentrism versus heliocentrism thing that I've been talking about, but it's just a really cool observation, and it's going to come into play whenever we talk about telescopes. He takes his telescope, he points it at the Milky Way. So if you've ever seen it, it looks like this milky white streak through the sky. You can't see that it's a bunch of individual stars, but if you had a telescope and you looked at it like Galileo did, you'd see that what makes the Milky Way look like this milky smear on the sky is that it's an incredibly large number of stars densely packed together from our vantage point that are so close together that our eye blurs them into a single object. We can't see them as individual objects. They can't be resolved by the naked eye. So he actually looks at the Milky Way and realizes that it's not some weird different object in the sky. It's actually just a large number of stars, all concentrated into an area in the sky. So Galileo's telescopic observations, really, really big ones. Notice that I have not mentioned retrograde motion of Mars or other planets. While retrograde motion is integral to understanding a geocentric model and a heliocentric model, you do not need a telescope to observe that. That's been observed for thousands of years before the telescope was even a thing humans could use. So while it is important to the story of heliocentrism versus geocentrism, it is not one of Galileo's principal telescopic observations that really allowed humanity to push past the geocentric model and go into a heliocentric view of our solar system. And that's not all he did. He also invents our modern way of doing science. So Galileo decided that we should observe nature to understand nature. No longer this Aristotelian idealism of you can logic your way to everything, that all fundamental truths about nature should be derived from logic and reason. He's not going to throw away logic and reason by any means, but he's like, hey, whoa, wait a minute. Why don't we actually see what nature is doing? Make some observations, come up with an idea of how nature works, a hypothesis, and then run some experiments to see whether or not the hypothesis works. Why don't we observe nature to understand nature? So he does a series of experiments to reveal some fundamental connections between things that are going to become important once we get to Newton. He is looking at how objects fall. So if you're going to go drop something, how does it fall? Whenever it was falling at a constant speed? Or was it speeding up as it fell, accelerating? Aristotle said that things fall at a constant speed. Galileo was like, I'm not so sure about that. Why don't we just actually observe it and do some experiments to find out if it's falling at a constant speed or if it's speeding up as it falls, accelerating. So he's going to make some fundamental connections between how fast things move, velocity, acceleration, and free-falling objects, and actually discover that they're independent of mass. So what are his major conclusions, his findings? And this is the idea, the popular story is that he dropped things off the Leaning Tower of Pisa, which he maybe did, but I think the more core of the experiments are actually rolling things down a ramp and using some geometry and some knowledge, easier to do it that way. But ultimately, he performs his experiments, he observes nature to test some hypotheses, and he finds out that free-falling bodies, so just gonna freely drop it, nothing's going to stop it from falling or slow down its falling, free falling bodies accelerate as they fall. So in 1 second, it'd be moving 10 meters per second. After 2 seconds, it'd be moving about 20 meters per second. Or to put it in feet per second, after 1 second, it would be moving 32 feet per second. After 2 seconds, it would be falling with a speed of 64 feet per second. So it's speeding up as it falls, it's accelerating. And more interestingly, is that the acceleration of a free-falling object is independent of the object's mass. It doesn't matter how much mass two objects have, they fall with the same acceleration. You drop a very heavy object, like a bowling ball, and a feather, assuming that there's no air resistance, if you drop them in a vacuum, they would fall and hit the ground at the same time. A cannonball and a basketball, you drop them both at the same time. One is much more massive than the other. They hit the ground at the same time. So the acceleration that an object experiences is independent of an object's mass, which seems rather counterintuitive. We're all actually going to work through this once we understand Newton's laws of motion and gravity. And we will see that this is a natural predicted phenomenon. Galileo did not predict this one, he observed this one. So objects are independent of mass. There are great videos in the unit slides that I encourage you to go watch. One of them is the Apollo astronauts. This was such a radical change to how we approach understanding nature that the Apollo astronauts took a hammer and a feather with them to the moon because Galileo predicted that if you drop those two things in the absence of air, here on Earth, a feather will fall and feel the air resistance is not in free fall. So they went to the moon and they dropped a hammer and a feather on the moon to show that they fall and hit the ground at the same time. I have that video linked in the Unit 1 Part 3 slides. Absolutely fascinating to watch. There's also a video of Dr. Brian Cox, sort of the UK's Neil deGrasse Tyson is maybe a good analogy if you don't know who he is. And he actually goes to a vacuum chamber, a very large vacuum chamber that they evacuate all the air from, so there's no air resistance. And they drop a bowling ball and feathers to see that they fall and hit the ground at the same time. That the acceleration is independent of the object's mass. And this sets the stage for what we're going to talk about next, which are Newton's laws of motion, because that's going to be the next player in our story of understanding how the planets move. Why do Kepler's laws work? What is the how of it? What is the physics? What controls and keeps the planets in orbit? Because Newton, more than anything else, is obsessed with understanding what makes the planets orbit according to Kepler's laws. What was the rhyme and the reason behind it? What's the physics? How is nature operating? And he's obsessed with that. And he was really inspired by Galileo's experiments of how objects fall. We were just talking about the observations that he had that things accelerate as they fall, and that it's independent of mass. The free fall acceleration is independent of mass. So to solve all this, to figure out why Kepler's laws work, he's going to do some pretty incredible things. And he does this while a rather familiar story. Turns out during the plague, people had to not go to university. They had to do something different, and they didn't have the internet, so he couldn't do these online classes. So he flees home, and while he's hiding out away from the plague, he was a student at Cambridge, he just sits down and, you know, what else are you supposed to do whenever you're at home avoiding the plague? He comes up with humanity's first laws of motion, Newton's 3 laws of motion, physical laws of how things move in general that apply to objects, the universe round. He comes up with our first idea of gravity, this universal force that is causing things that have mass to pull towards one another, the thing that is keeping us rooted to Earth, the thing that's making Galileo's things fall at an accelerating rate. He comes up with humanity's first concept of gravity. And to do all of these things, to do his laws of motions and to understand gravity, to make sense of Kepler's laws, you know, he has to invent an entire new branch of mathematics called calculus. That's what I do in my free time. I invent calculus while I'm age 26, while I'm fleeing the plague. So Newton was clearly a genius. And we will pick up with Newton the next time. I have to do some background work, strap in. We're going to talk about some physics terms, but it's all so we can have this deep understanding of why things orbit, how things move in the universe. One of the most powerful pieces of knowledge you can be armed with, if you think about it, because we're starting to understand how things in the universe move. All right, I'll see you in those videos.